Good morning, everyone. So, in the last class, we have seen what is the content for this course machine learning for image processing. So, in this class, let's get some introduction to what this course could contain. Let's see that in bit more detail in this class. So, for that, let me ask you some questions, and I'm expecting some possible answers from you. So our course name is Machine Learning for Image Processing. There is a machine learning part. There is an image processing part here. What do you think is this machine learning? What is learned by the machine? That's the question, I think, more appropriate question. What is it going to learn? I want a very simple keyword like answer. What is it going to learn?
It will learn from the data input,
My
all the
question,
data
yeah,
that
no,
we
no,
are
no, no,
inputting and
no.
make decisions from that.
Yeah, just pay attention. I am not asking you from which it learns. I am asking you, what is it going to learn? Hope the subtle difference between these two questions is clear to you.
Sir, it will learn the how to analyze that particular data to get a particular result which we desire.
It can be more precise. Your answer could be more precise. How to analyze and all. Finally, it is going to, there is nothing like a discretion that it is having like we have, although we call it artificial intelligence and everything. There is something, it can be more precise.
Sir, is the question what is learnt in machine learning?
Yeah, what is it that the machine is going to learn when we are saying machine learning?
I believe that it learns a function that maps an input to an output.
There is no function as such. This is not any analytical modeling where you have a function.
Sir,
Yes.
is it that features how they are interdependent and how it is affecting the output? Is it so?
Yeah, somewhat close to the answer. The way I would put it is going to learn a pattern that distinguishes. It is like it is going to learn the signature. Assume that, for example, you want to do a classification. The machine learning, we call it as a machine learning because your machine is going to learn the unique signature of each class in a way that it distinguishes it from the other class. It is going to learn the patterns, unique pattern that distinguishes one from the other, or a unique pattern that characterizes based on the task you want to do. Would you like to contain this definition or add something to this? As I said, some of you had mentioned the features, partly true. I'll come to that as we move on. Okay. So that's also, this pattern can have a set of features, but still you do not know which all features and which combination of features. That is what this machine learning is doing it. Because if it is learning a feature means assume that in our class, let's say, how diverse is the class in terms of the geographical locations from India. Assume that I don't, this was not given in any of your forms that you have given, but I would like to make an analysis of it based on how you look in an image. I'll take an example of an image because anyway we are going to do the image processing. Assume that I have your pictures of you. Say, then I want to, let's say, let's say in the whole institute, out of those institute, 80% of the population, I want to take it as a data set where I know to which state each one of the respective student would belong to. And from that, the rest 20, I would like to make an guess there. So what it will do at the end? What could I give as an input to it? For example, I could give it what is the height of the person. Okay, height alone will not do. This is one feature. Height, what is the height of the person? Assume that I have taken pictures at same resolution, same physical pixel spacing to physical spacing mapping and all. How is he built? Is he thin built, well built, or whatever it is? So built of that person, assume that whether he has a mustache or not, whether he has a beard or not. Maybe that also assume that I am taking it. Maybe assume that I have also other things, food habits, let's say. Those are also, since if you want to just restrict to image processing based, you can forget that for a moment, or otherwise they can also come. So all these, each one of them is a feature. Now what I want to do, I want to, so I am talking about a problem of classifying a given student into one of the states of India. So each one is a feature. So this is the terminology we would be using it. Okay, so pay attention. Although this looks like a very generic class, we are indeed introducing the terminology required for the rest of the classes. So pay attention to that. So each of them that I'm considering here, what is his height? How is he built? We refer each of them here as a feature. Okay, and to this, that's what we refer to as a feature. The whole thing we refer to as a sample, because the state, each state, we are having one sample. Each of you are a sample for one particular state. So these are, the whole feature set is something that is characterizing you. So this is referred to as a sample. Each element of it is referred to as a feature. And of course, the sample also, you could also refer to, if you want, as feature vector, if you are representing the whole thing as a vector of multiple features. Now, assume that I want to get the statistics, or a new sample has come to me. That means a new person, new student has come to me. I have, out of all, how much, let's say 1,000 students, 800 students, I know each one to whom it belongs. Now what is it that I can feed? This features I would feed and tell that he belongs to, let's say, Punjab. Another one belongs to Maharashtra. Another one belongs to Andhra Pradesh, Telangana. So I give you this feature vector and also tell it what is the state he or she belongs to. Now what could happen? You could represent this whole thing. Assume that my feature vector is of dimension L, capital L. I could represent the whole thing in an L dimensional space and let that learn. This is again based on the assumption that there is a unique pattern that distinguishes this feature vector. I consider is good enough to capture the variations that exist among different people coming from different states. That's the assumption. Okay, if that a very assumption is wrong, then of course nothing can be done here, but that's the basic assumption that we are starting with. So then what you could do, you represent it just like in an X and Y space you represent. Now you represent these sample points in L dimensional space. And now you know for each state where those points are there. And then you will try to, in the first initial parts of this course, you would look at, can I model the distributions? So for the whole state, I have some samples. From those samples, can I model the probability distributions of that particular state in this L dimensional feature space? You do that, and based on that, probabilistically you do to begin with in this course. And as you move on for the next linear classifiers, non-linear classifiers, linear classifier is something. So for a simple case, consider I have only, let's say I'll just look at what is the height of that person. Okay, and maybe if what is the build of that person, is he thin built, medium built, well built? Okay, assume that for some very strange reason. Okay, this is, don't take it literally. Now suppose there are just two states I'm considering. State A point, what I will do now, height and build I know. So for this height, he is having a particular build, he is there here. Or build also, I assume that I have a scale of 1 to 10 build, not just 3. Okay, suppose one state, from one state all students have come here, another state the students have come here. So then I would say this could be a linear separation is there in this space. Okay. And then if some new person comes, let's say that new person has come here. So very likely I will put him into this state. This is a classification problem we are talking about. And now you use your machine learning algorithm. The job of your machine learning algorithm, what does it learn? It learns the pattern that uniquely distinguishes or represents or characterizes your object of interest. Your object of interest here is a class. On the other hand, this object of interest could be a single person itself. Okay. Let's say there is a person by name Ramesh in your class. Okay. Suppose I want to find him. How could I find him? I called another student from your class and I asked him, there is a person who is well built, who is tall, who has brown eyes, who has curly hair, who has a mustache as well as a thick beard, who has spectacles, okay, so on and so forth. So all these, each one of them are the features, and the whole thing is a feature vector, which is pattern. It's a pattern that uniquely represents that particular person. Any questions, comments, or doubts here on what is learned in machine learning? Then the next question is, what for is it learned? Okay, you want to do machine learning. Maybe it looks too trivial, but it's okay. You could still answer that. What for is the machine learning these patterns? There
To
should be some
categorize,
objective. Hmm?
to categorize things.
Yes, to whatever job you want to do it. For example, it could be you want to classify all the things you could, all applications of machine learning can come and sit here. So it could be segmentation, classification, some any inferences you want to drop. The list, we will anyway see some applications of that a little later in this class itself. The next question is, how is it learned? That's all we are going to study in this course, right? A subset of methods for doing this is what we are going to study. The rest of the content is trying to eventually answer this question. Okay. Now, how do you distinguish? I'm sure you have heard all these buzzwords of machine learning, deep learning, artificial intelligence, pattern recognition, statistics. So how do you distinguish? You have a course on another course is there after this hour, which is on deep learning. This course is on machine learning. How do you, maybe let us start with machine learning versus deep learning to begin with. What are your thoughts about it?
In deep learning, feature extraction is done by itself. I mean, no human expert is needed. Whereas in machine learning, someone has to define features.
That's, I think, that one of the convenient or common definitions. Good, very good. So that's one way people distinguish machine learning versus deep learning. Again, maybe in the interest of time, let me just answer. Look at it, you will see people drawing some Venn diagrams kind of thing, as I think Rajesh, I guess, if I'm not wrong, I could not see the names as mentioned. They say there is this AI, okay, artificial intelligence. In that there is ML, in that there is DL. Okay, so DL is a part of ML. That's one answer, which is in fact one possible answer there. It is a futile exercise to actually come up with clear lines of demarcation between machine learning, or among, if not between, machine learning versus deep learning versus AI versus pattern recognition versus statistics. Okay, don't fall prey into figuring out what exactly it mean. The reason why I would say it's a futile exercise is people started using it in different ways, but typically people started with AI. Initially there is a lot of buzz around that in 1980s and all. Then it reached a kind of a saturation point, or even a kind of, in public you could say, a suspicious point where it is promising, it is too ambitious and promising too much than what it could deliver. So then machine learning, deep learning and came. And for us, at least for this course part, pattern recognition is you can also call this as a pattern recognition, whatever we are doing here. As I said, that's why I started with this question of what is learned in machine learning. You are learning a pattern that uniquely characterizes certain or gives a unique characterization that is useful for the task that is needed for the task that you want to perform. So obviously pattern recognition is part of machine learning. I will go into a block diagram mode and explain you. There you would realize pattern recognition alone is not the job there. You have a features, you generate these patterns. Okay, all these other steps are also there. So that's what I would say, machine learning and pattern recognition. Deep learning is, you have one very good definition that one of you has mentioned is the feature vector is something you are deciding here, and that is also high level features are also learned from the input feature vector. So maybe still this is very abstract for our practical purposes. So for our practical purposes, you could think of the distinction as when you have too many layers there. Okay, when the number of layers, for example, take the case of convolutional neural networks, where you have the encoder block, decoder block. There are many deep layers out there. Your learning is very deep there. So that you refer to as deep learning, as in that Venn diagram or whatever you call it, as it is shown. We will not venture into that. We will actually touch upon and get an intuition at the end of this course, but we will not focus very much on the deep layer based models and architectures. That's where the deep learning comes. Well, statistics is always the backbone for all these things, which would hopefully become more clear to you as we move on. So how do you distinguish image processing versus computer vision?
For an image processing, we modify image, like we give input as an image and get output as an output as image. But in computer vision, what we do is input is going to be image, output can be any action or any data, something like that.
Very good, very good. So we have human vision, for example. What do you mean when we say we have a human vision? It's not just about looking at the image, but we draw inferences out of it. So when you make inferences out of the images that you see, you refer to a computer is doing now. It's not the human that is doing. A computer is doing this. Suppose you are just taken few pictures, 2D pictures. Now your computer is able to reconstruct the 3D object. That's a vision. It's not just the image. From that, it has inferred what the object is. It is able to reconstruct that. You have a video where you are tracking, let's say, different vehicles in the traffic. You put a video there. You have fixed a camera there and you are doing it. So you are tracking where that particular vehicle has moved from frame 1 to frame 2. So you are making some inferences there. Image processing, as one of you has rightly mentioned, typically you are processing the image, which means conventionally you could define it as your input is an image and output is also an image. Then you put it under image processing. Don't stick too much to these definitions again. I'm making these distinctions for our working purpose. Okay, what you could expect, these are all I would put under working definitions. And particularly in this course, when we say image processing, typically one thing we consider this problem is a classification, image classification problem. Okay, so here you could contend with me that while you are classifying, it is not just an image. Well, in the classification, each sample or each pixel to which it belongs to which object or class it belongs to, we are going to say. So classification problem, segmentation problem. Again, don't go by strict sense. Segmentation is like identifying a particular student in a class. Classification is like you classify the students into different based on their states or whatever it is. Okay, classification, segmentation, then denoising of the image. So your input is an image, output is an image, but there is a noise that got added to the image that you have captured, and you are removing that noise. So image denoising, deblurring. So these are the applications that will be considered in this course. Okay, hope things are clear. Well, this also would help you to realize that don't stick too much to any of these definitions. Exaggerated, it does have an element of truth in it. So when you are implementing, you call it with the technical names like logistic regression and all these things. But when you are hiring, you would say that I need people in machine learning and other things, and you are writing a project as a faculty or someone else in a company, you are asking for some, or you are raising, you're doing a fundraising as an entrepreneur, then you would say I work in AI. But as this is it's a cartoonized version of the truth, but there is indeed a profound truth in it. There is statistics at the end, depending on the way you frame it and your audience, you keep changing interchangeably using these things. And anyway, for the rest of the course, we will anyway see the importance of machine learning, the vast, profound contributions that the machine learning has done in various domains, be it in computer vision, be it in medical imaging, be it in finance sector, you name it, everywhere it has a very strong footprint. Machine learning does have a very strong footprint in various domains. Okay, it in fact spread like a wildfire, and it does improve the accuracies and the quantitative results that you would get by a long jump. There is no denying of that fact. But at the same time, there is a hype around that. There are certain myths about that are kind of hardwired even into people from academics, or even many. Nobody is an exception. So you should tread the path with a word of caution. Since anyway we'll be highlighting the importance things later, I would only tell you some cautionary posts are what I want to show you. By the way, I have given you a link here. This is an ACM India in a India webinar series. There was a talk by Professor Jayant Haritsa. He is a professor from the SERC Department of Indian Institute of Science, Bangalore. Data science and astrology, is there a difference? Okay, that for catchiness there is some astrology and all, but that's one of a very nice talk that gives you a balanced view and balanced comprehension, which is in these days of hype is very much required. So you need to just register, and then you will be able to see. It's around a 1 hour talk, so please do watch it. By the way, although it talks about data science, it does have very similarities, and all those inferences are almost very much true in case of machine learning also. So the next few slides, I'm not going to repeat that. I just take few important slides from it. Okay, so please, anyway, I would strongly or highly recommend you to have a look at that talk. Okay, so since it was in data science, it's equally true for engineering as well. It's not just about science. Look at how things evolved over time. There were times when you used to observe data, okay, and based on that, you used to come up with models. That's an empirical one. Then, for example, you do chemical reactions, you mix two and see what's going to come. And based on that, that's a science example. But you could very much do an engineering example in similar lines. Then there were, again, there were all these things in each time, but this is a kind of predominantly what was there. Then there were things like you have theoretical models. Then there were, for example, the gravitational law, or the theory of probability theory that we are going to discuss in the first 1/3 of our course, which tries to explain or model. And there were, you do a lot of simulation work like fluid dynamics and see, and then make models. But now we are in an era or is where you have the whole data. From the data, you are going to make inferences. The roles have got interchanged here. Okay, so you are exploring data and making that. So this is something is not very common. So that's something we need to keep in mind. And I think this is a very very important slide. How can I master machine learning? So magazine did it for data science. What they figured out is 44% of people said you need to have a good command over Python. Okay, you replace this Tableau and RStudio with something else like PyTorch or whatever other integrated developing environments are there. So understanding or impression of machine learning in not only general public but in quite a few technical people as well. So then you would also see similarly what you see for data science nowadays. Also you would see that data science boot camps become a master of machine learning in 3 months, that too on weekends, just 2 days. And then what will be the outcomes of that? They will say master all 3 elements of data science: statistics, tools, business knowledge. So machine learning entrepreneurships also, you would see they would also surprisingly help you on how to craft your CV and reach you to the right job opportunities. And the myths here are, here also say machine learning driven, data driven. So data is the new oil which you burn and get the light. Okay, and machine learning is the new quantum mechanics. And this is what Professor Jain Haritsa himself tossed it, is like ABCD. Anybody can do data science, like anybody can do dance kind of stuff. So this is how people are thinking. We just need some courses on 3 months, we can not even full 3 months, and then you would master all those elements. But what people forget is, in data science, there is a word. It is not just about data. Although it's but the myth on the other hand is that that's the new oil. You have more data, you can model anything. But on the contrary, there is a science there. Again, that word also is something that can be contended. There is no science in data. Okay, it is not in that perspective. It has to be seen. It has to be seen in the perspective that you use scientific methods. That's why that science is there. Scientific methods to analyze and draw inferences or learn patterns in that data. So it does require, just like data science requires physical mathematical principles, data domain, not just programming environments. Okay, and there is a famous quote by a Nobel laureate that tells, if you torture the data long enough, it will confess to anything. If it is not giving models, you change the parameters of your model or change the data set, it will yield you the results that you want. Okay, so this is the reality. You cannot be a machine learning expert in a short span of 2-3 months by just learning Python or learning MATLAB or some other tool. Not enough, because as a backbone, it does require a very deep understanding of the probability, statistics, in particular pattern recognition concepts that have been developed over a period of time. Otherwise, as we have seen a video in the last class, it could eventually end up like that. And blindly going through, this is one example. There were again tens of examples here, but I just took one again from his one. Suppose this is the linear regression. You will see it, this regression and all in this course, as well as perhaps in deep learning also, which tells you here, gives you the year here, and on the Olympics for men and women, the time that they took for completing 100 meters running. So this is the data for men, this is the data for women. You do a linear regression fit here and see, and from this simple model you can draw very crazy and unrealistic differences there. For example, the slope here is more, so it could tell that on so and so year you just extend these lines. First, crazy, or it may or may not be true, but doesn't intuitively make sense, is that women, since the slope here is more, although they were taking more time at this beginning, there will be in so and so year, in 2156, women will beat men for the first time in terms of the time they take for completion, while currently it is more. So intuitively, I don't mean it cannot happen. Intuitively, it doesn't mean by looking at the values here and just extrapolating it by slope will give you wrong outcome. And even more wrong outcome is you could keep projecting this line extended, and there comes a time when in a less than zero, so you could finish off your the 100 meters running race in minus 20 seconds, which doesn't make sense, right? So ignoring reality, simply working on data ends up nowhere. Okay. And this is one example. There is summer, you eat lot of ice creams. There are sunburns also. Assume this is a more in countries where you have this issue, right? So then eating more ice creams will increase sunburns. Your data, when you are learning it, it might end up giving you such conclusions. Or maybe let me give a more contemporary example. Because of this COVID restrictions and curfews, there were restrictions on the people moving out, right? There was work from home has been there. Very few people are moving out in the beginning, first wave and second wave. I'm not talking about currently. But then you could say, because people are staying at home, thefts have decreased. And because people are staying at home, there were no accidents happening on the road. So drawing conclusion like because of COVID, okay, if you just see the data and draw interpretations, you could say because of COVID reduces the number of thefts at home. COVID reduces if more people are affected by COVID, there will not be any more accident deaths due to accident. I can draw, your model will give you that. Nothing stops. This is absolutely what you will get with your data-based approach, data-driven approach and everything. So what would be missing there is the domain knowledge. So it is very important that ML is a support. ML is a support, not a substitute for domain knowledge. This you have to see in the context of the problem, and you have to correlate it with the intuition and the reality and the domain knowledge which you have it. Don't throw it away and think that ML will rule everything. Okay. Similarly, as I mentioned, good understanding of math basics is essential to become a good machine learning expert. These areas include random variables, linear algebra, and vector calculus to begin with. Then graph-based stuff are there. There are quite a lot of things. It will overall cover quite a lot of mathematical areas. And another important point would like to mention here is don't rush and end up as a blind practitioner of ML. What I mean by that is you may end up, if you just learn some Python libraries, okay, then you know how to feed the data. All you know is to read and feed the data and then look at the output. Then you will become a very blind practitioner. If there is some issue, if it is working for a particular data set acquired from a particular site, and there is data coming from another site, not working, you don't know what to do with it. Machine learning model is very memory hungry. Okay, it is consuming, you need to give a workhorse workstation there. It is not practical. Your employee would ask you to come up with a small, you give, I don't can it be reduced or can it be scaled down? Unless you know what like the nuances of it, you won't be I'm not even talking about somebody who would make breakthroughs in machine learning, come up with new models. I'm just talking about a practitioner who has some good knowledge to understand and to make sense out of it. Even to do that, there is no way you could rush and get it. Okay. So then again, this is rightly kind of supported. These statements are supported by the recent trends. If you look at it, it's more towards explainable AI, artificial intelligence, or interpretable AI, or how do you combine the domain knowledge with AI, or the amount of computational resources required. Are they will also very interesting things you would come across if you look at the carbon footprint created with machine learning, all these things. And again, they are in many cases make it work in multiple environments with minimal expenses. You need lightweight MLDL models that can be run on a small embedded platform. So lightweight ML and DL models. And of course, then this list is by no means exhaustive. You can also add other topics like you have very minimal data. With that, how can you do that? So all these things, you don't want so many layers. Can you still learn that? And as I said, there is a need to combine the domain knowledge with machine learning or deep learning or whatever you are going to say. Okay, I will take a pause here. So any questions or comments before we proceed with the machine learning for image processing? Just would like to emphasize here that the applications are not just for image processing, as you would be doing in other courses. Machine vision will come, and again, some of these applications you could put under the basket of machine vision itself. Again, they do have a different definitions for machine vision versus computer vision. Let's not go into that. Optical character recognition, one of the earlier applications of computer vision. Then in particular in medical imaging, computer aided diagnosis, the contributions made by machine learning in this area are in particular in some of the applications are phenomenal. Okay, then with an accuracies that were earlier were hard to even think of. Then speech is another important customer that has various machine learning applications. And in fact, many machine learning applications, new methods have models have come up from the area of speech. Speech recognition is just one thing we mentioned there, but there are speaker recognition, speech recognition, speech translation from one language to another, speech understanding, speech to text conversion, you name it. It's a very huge field in demand. For in particular in India, this has a huge potential for machine use of machine learning. For example, because we have so many languages, so these days it requires a lot of engineers who could contribute this to this field of real-time translators from one language to the other language, or that language to the text, or you recognizing the speaker, or speech is under a very noisy environment. So how do you denoise that? All these things are there. Then again, just like speech, face recognition based, there are many applications. It's not just about face recognition, it's detection, tracking, a lot more things you could say. And then in biometrics, by biometrics, it could be fingerprint is one biometric, iris is another biometric, signature verification, a signature, it could be an offline signature on the documents that you may do with a pen on a paper, or it could be these days these online signatures for banks. So doing a lot of applications of that are there. Then image database retrieval, data mining, bioinformatics, we could keep talking about each of them for even if you just briefly touch upon the subtopics on it, each one would take around 10-15 minutes. So this is just to show you, or just to illustrate you the large canvas that this machine learning has. Okay, so with that, maybe I will stop here. I already introduced these words. So feature is a measurable quantity obtained. Yeah, again, the way pattern word is used here is in a slightly different way. All I would say is a measurable, observable quantity that you would use as a part of your feature vector, or as a representative of your sample. As I mentioned, it could be the height of a person, weight of a person, and all these things. So each one would be one feature, and the whole thing you could call it as a feature vector or a sample of a particular distribution when you know the ground truth. And these are referred to as not random. Since it's a vector, these feature vectors are treated as a random vector drawn from a sample of a particular class. Okay, this is how we define feature, sample, and random process there. So maybe I will up with this slide. Okay, say for example here the features could be, you are looking, there are two images, may assume that these are the tumors, images of tumors of a particular part of your body, and let's say one of them is a benign tumor. Benign tumor means there is a tumor but it is not dangerous or cancerous. There is a similar tumor which is malignant, they refer to as. Now assume that for a given image you are taking two features, mean intensity of that image and variance of that image, and assume that you are plotting mean and variance on two axes. And you know, for example, this is something, let's say you are representing with a circle here. So you have a whole set of images. So as I said, this is one sample. Such samples, let's say you have 10 samples for this class, 10 samples for this class. So the whole objective here would be to plot them, and assuming here the very assumption is these two features are good enough to distinguish one class from the other, and that pattern which distinguishes is either inherently or implicitly learned by the machine learning algorithm. So you plot them, all these circles for benign, all these cross marks for the malignant tumor. Now when a new sample comes, now what you do not know is from which cluster or which class it is, you do not know, but you plot it and assume that you have come, once you have these ground truths, and based on these circles and crosses you would have drawn this line, okay, boundary line that distinguishes between these two classes, and depending on which side of it is there, now you can classify. This is what machine learning classification does. Okay, we'll stop here at this slide. Okay,